Hey, Alex, welcome. Morning, Tanner.
Morning.
Morning, Jeremy. Morning, Kellen. I think I love that name too, Kellen. Morning, Ben. Sophie, hello. Welcome. Cameron, good morning. Willa. Pablo, welcome. Ashna, hi. Sorry,
Is this an early release day or not?
I don't think so.
Was it ever? I have it on my calendar. It's an early release. I mean, it says on there, early release 10/23.
Is it on our Google Calendar?
I don't know. I didn't look at the fucking Google Calendar. I just looked at the one that they gave me that I printed out.
A little bit.
So you're saying no, it's a regular day?
Well, let me check the calendar.
Because I didn't think I had a lab today, so I had everybody come yesterday.
We have end of first quarter ends, B-Day. I don't have anything that says early release. Welcome to live Zoom rooms, where even the adults have slowly lost their minds. Tune in next week when, who knows what's going to happen next week. All right, folks, I may have missed some of you there while we were being entertained by our visitor. So welcome. Good morning. I'm glad you're here. It's nice to see your face, whatever faces I can't see. Keep on logging into those Pear Deck slides. You're going to want those today. This is our plan, or this was our original plan, although there was a request yesterday from the first hour folks to once again look at how you would analyze the data for lab number 6. I sent out a text and I posted a Google Classroom message that as I was looking at some of your work for lab 6, there were some statistical analyses that were missing. So really I'm asking, would it be helpful to spend a few minutes here at the beginning and kind of skip our check-in and instead use that time to look at, once again, how to analyze the data for lab number 6? Thumbs up, thumbs down. You can put it in the chat. I'm seeing more thumbs up than thumbs down right now. Now I'm seeing even more. Okay. So it won't take too long. I just wanted to make sure that, when we do things in class, there's a reason why we're doing them in class. We want to be able to use them in our lab write-ups or on our assessments, and they don't exist in isolation. So rather than doing our check-in, which we can just move to another day, really it was kind of a fun one. I was going to ask you to get up and do a quick scavenger hunt around your house for a random object. And the first one back was going to get, a special prize, but we can do that again some other day. We'll do a sample analysis instead. All right, let me stop sharing here for a second and pop over to the lab. And let's see, we want lab 6, don't we? Yes, we do. Oh, and people are popping up. Let's see. Alrighty. This over. Share the screen with everybody. Oops. All right, so my hope is that this spreadsheet looks familiar at this point. This is my sample spreadsheet created for all of you. So of course your goal was to choose a set of variables, a pair of variables that you could compare to one another to look to see if there was a significant relationship between the two of them. Well, in this case, when we say significant, whether or not there was a linear relationship between the two variables. And of course, in context, this was to begin to think about in the respect to animal behavior, right? So if the animal is doing something, right, in respect to something else, is there a strong relationship between those two variables? So you had different ways you could manipulate the bee, you had different ways that you could manipulate the flowers in this virtual environment, and you were looking to see if there was a relationship between the two. So with my sample data, I'm just going to use one set. I put 2 different examples in there, not because you had to do 2 different examples, but because I just wanted to show you 2 different ways that you could generate data through the simulation. In this first one that I did, I manipulated flower distance, the distance the flowers were away from the hive, and I had the 2 bees, and I kept them with their default settings in respect to foraging time, 50 seconds for B1 and 100 seconds for B2. So I collected all of that data directly from the simulation, literally just copied and pasted it from the simulation, and then I graphed those data. Okay, so we've got a scatter plot for both B1 and B2. Best fit lines, trend lines were generated or drawn by Google Sheets through those data points. And of course, we can use Google Sheets to calculate the R-squared value or the correlation coefficient. Now, like we talked about in class, the correlation coefficient, the R-squared value is not really of meaning to us. It's the R value. So what we want is the square root of R-squared. So I'm going to go ahead and grab my trusty calculator, which is my phone in this case, closest one that I've got. And let's see, I need to turn that off. So I'm just going to do this for one of the bees. You do the same thing for the second bee if you wanted to, but I'm going to take the R-squared value 0.799 and take the square root of that, and that's going to give me an R value of 0.89. Okay. So in this case, R equals 0.89. Now I will say, in reality, that's negative 0.89, right? This is an inverse relationship. As flower distance increases, the collection rate decreases. But for the sake of our analysis, we can just take the absolute value of that particular value for R, okay? So once you've got that value of 0.89, really what you want to do with that, right, is you want to test it statistically. And to do that, you first have to consider the null hypothesis. And we talked about this last week. The null hypothesis is a simple statement that there is no relationship, no correlation, no effect. You can phrase it in different ways between the 2 variables that you are comparing. And what you're attempting to do, right, is through the statistical analysis, either accept the null hypothesis or reject the null hypothesis. Something that came up yesterday is that it doesn't matter if you're accepting it or rejecting it, right? You're not, sometimes I use the words like what we're trying to do is, that doesn't mean that it's more correct or that it's the right way to do this. Sometimes the data are the data and you just gotta go with it. If the data are not allowing you to reject the null hypothesis, then accept it, you're fine. If you can reject the null hypothesis, that's okay too. There's no right or wrong here, right? You're not gonna lose points, for example, because you were forced to accept the null hypothesis, okay? All right, so our value of 0.89 is an important one. I'm gonna go ahead and clear that off. And I'm gonna switch over to our slides because with that value, I actually would like to do something with it. So I'm gonna scroll down here to our trusty values for R. And I will once again share my screen so that you can see this. You think how fast I'm getting with this, right? Practice makes more better. So we want to take the value of R that we've calculated, or really the Google Sheets calculated for us, and compare it to a known critical value. These values will always be provided to you. You know, they're going to come from the slides, probably. I guess you could Google this if you wanted to, but I tried to import multiple images of this table into the Unit 4 notes so that you could use it. But what we want to do is compare our calculated value of R to our critical value, but we want to do so at the correct number of degrees of freedom. I believe there were 7 pairs of data that I collected. So the degrees of freedom will simply be n minus 2, or the number of pairs minus 2. That would give us 5 degrees of freedom. Scroll on over, our critical value for R is 0.754. If you remember, the calculated value of R was 0.89. So with that information, go back a little bit, sorry. With that information, there it is, right? Since our calculated value of R is greater than our critical value of R, we can reject the null hypothesis. And we can say with confidence, right, really with 95% confidence, if you will, that the relationship between those variables is statistically significant. We can't completely eliminate the possibility that chance, that natural variation is playing a role in the outcome of our experiment and the comparison that we're making, right? That p-value, if I were to go here, right? That p-value of 0.05 always allows for, in this case, a 5% chance that it actually is natural variation that's responsible for the relationship. And this is why we talked last week about you can't prove anything in science. This is one of the reasons why. There's always an underlying chance, right, albeit a small one, that natural variation is playing a role in the outcome or in the comparison that you're making. Okay, but in this case, since 0.89 is greater than 0.754, we can reject that null hypothesis and we can accept the alternative hypothesis that there is indeed a relationship between the two variables. And that's what you're striving to do in the lab write-up. So if you haven't had a chance to do that, feel free to unsubmit your work, make those revisions, and then resubmit when you're done. I will take a look at your work probably over these next couple of days. I've started the process for a lot of people, but not for everybody. So feel free to make these revisions if you need to. That was a lot of me talking. What questions do you have?
So if it's always greater than the critical value, then you can reject the null. Because on that notes, like we were supposed to read for that chi-square thing, there's like a line and then it had like reject with an arrow going one way and then like accept the other. So what does that mean?
That's a different way of displaying the greater than or less than. And we're going to get into the chi-square test today. It's a different type of statistical test. Luckily, the same process that we're using to either accept or reject the null hypothesis is going to be in play. But that table on the line that you're referencing, Jeremy, really is in respect to if the value now of the chi-square statistic, so not R, but the chi-square statistic is greater than the critical value of chi-square, we're going to be able to reject the null hypothesis. That's going to be on one side of the line. If instead the value of chi-square that we calculate is less than the critical value, we're going to be on the other side of the line. We're going to have to accept the null hypothesis.
Okay.
Yeah, that's what's coming up next.
I have a question too.
Of course.
So let's say my R square value that I got when I plotted things in my lab was 0.
Okay.
So I already know that like R is going to be 0. Do I still need to say R is going to be 0 and all the other like null hypothesis things in my like like explanation? Because I was super brief this time because there was no relationship and I just didn't really know what else to say.
I think that even in a couple of sentences in your evidence section, it would be worth reporting the R, reporting the critical value of R, in this case, obviously saying that R is less than the critical value and that you're going to have to accept the null hypothesis. But that's just going to be a couple of sentences. And then when you go to your explanation, right, we're still trying to connect the evidence, in this case, that there is no relationship between the variables, to our science idea, which for most of us, for most of you, is going to be that transmission of information, both between and within biological systems, leads to change within and between the system. Well, in this case, whatever information is being transmitted, right, it's not influencing the behavior of the organism, right? It's not changing the behavior of the organism in a statistically significant way.
I have a quick question.
Yeah, of course.
I got it so that there was a relationship that was significant for one B, but not significant for the second B. That's good, but that means I had to put it in my claim that it's significant for one and not significant for the other.
And unless your question, right, was addressing just one of the B's.
Okay.
Which is totally fine, right? You know, what the claim is trying to do is answer the question. So if your question addresses two B's, or doesn't make it clear that you're only addressing one B, and then in your claim you're only addressing one B, well then your claim would be a little vague or unclear relative to the question that you posed.
Building off what Tanner said, I also had one where one of them was statistically significant and one of them wasn't. I went ahead and said that they were both not, there was no relation in general between my variable and the other one, because you can't do that.
Well, if you're finding a relationship for one B and not for the other B in your explanation, right? Since once you identify what's different about the two B's, it's probably the foraging time, right? Yeah. That's informing why there's a relationship between the variables for one of the B's, but there isn't a relationship for the other B.
Okay.
Anything else? Okay. So again, you're welcome to unsubmit your work. I think it's the button on Classroom. Make revisions, make edits if you need to, and then resubmit when you're ready. You won't be penalized, right? This is a process. This is how we learn. If I'm going to be punitive, learn, that doesn't make a lot of sense. All right. It would depend on which lab. I have a question in the chat about revisions to the lab. Technically, lab number 6, this lab, was due on Wednesday, right? So if you're making revisions to the lab, that would almost require that I've already assessed everybody's work, which I may not be able to do by the end of the day today. So if that's important to you, just let me know. I know 12th graders have transcripts that are going out to colleges, and I will make sure that the first quarter grade reflects your best effort and your best work before grades are sent to colleges. For 11th graders, really, it's the semester grade that's important, not so much the first quarter grade. All right, was this helpful? Okay. Are we ready to move on? Okay. So, oh, sorry, another visitor popped into the room, this time with less profanity. The early arrivals understand that reference. The late arrivals show up early. You never know the show that you're going to miss. All right. So the rest of the agenda for today deals with introducing a new statistical test that uses a different type of data. You might remember from last week that we've been analyzing continuous data, right? Data that's collected over the course of time. But there's another type of data that biologists often collect. It's discrete or categorical data. And we want to look at a statistical test that we can use to analyze that type of data. And in fact, I've got lots of different practice problems that we can use, and I'll do one together with you so I can show you how this works. I've got one that comes right from a released AP exam. But I've got another where we can actually go back to the Hardy-Weinberg lab number 5 that you did a week or so ago, and we can use the statistical test to determine if there's a significant effect of a variable that you may have manipulated as part of that virtual simulation. You may have actually even wondered, I know some people even asked, do I have to analyze the data for lab number 5 statistically? And if you asked that question, I said no, because, well, in reality, you hadn't yet learned the test that's necessary to analyze those data statistically. So that's the plan for the rest of today. We will take a break, don't worry, and we'll wrap up things before you sign off with a quick exit slip. Alrighty, so we'll do a quick intro to the chi-square test, then we'll take our break, and when we come back, we will do a practice problem. So just really briefly here, I mentioned a moment ago that there's 2 different types of data that we might collect through our experiments as biologists, right? There's the continuous data, which is those data collected over the course of time, and we've been analyzing those data really since the beginning of the year, right? These are our error bar analyses, right? We do our graphical analysis. This is our linear regression, correlation coefficient analyses, the ones that we just went over here at the beginning of class. But there is another type of data, discrete or categorical data, that we often encounter as biologists. And what's different about these data is that rather than being collected over the course of time, these are data that are collected these are data that are collected at one moment in time. So they might be the number of observations. They might be the number of organisms that look a certain way or are behaving a certain way at one moment in time. So a discrete moment in time, rather than over the course of a longer period of time. So there's a stark difference between the 2 types of data and how they're going to be analyzed. We can't analyze continuous data with a chi-square test, and we can't analyze discrete data with a correlation coefficient or with graphical analysis. It doesn't work. Okay. So the test that we're going to learn a little bit about today before we take our break, it's called the chi-square test. You already read about it. Hopefully had a chance to look at those 2 practice problems, look at the answer keys that I posted to make sure that you were doing it right. This will be a quick introduction, and then we can dive into a practice problem after our break. Okay. Whoops. All right. So the formula for the chi-square test will always be given to you. You do not have to memorize it. It is part of the AP formula sheet that might be part of the AP exam in May, whatever the exam looks like. And in essence, what we're going to do with the chi-square test is we're going to compare 2 sets of values to each other, an observed set to an expected set, right? But both of these sets of data are discrete, right? They are observations. They are numbers of organisms that have been measured at one moment in time. And ultimately what we're asking is, okay, is there a significant difference between what we're seeing, what's observed, versus what we would have expected? Okay. And I'll say up front, the expected values are often the most challenging values to come up with. So we'll spend some time here after our break thinking about how you would go about doing it. But what's great about this, and Jeremy referenced this just a few minutes ago, when we do our analysis, we're going to do it in the same way that we analyze the data for the correlation coefficient for our linear regression. We're going to calculate a chi-square value. Okay. We're going to compare it to a critical chi-square value. And if the value that we calculate is less than that critical value, we get to accept the null hypothesis. If the value that we calculate is greater than the critical value, we have to reject the null hypothesis. So even the null hypothesis part is going to be the same. You know, in this case, we might be asking or opposing the null hypothesis in such a way that there is not a significant difference between what we observed versus what we would have expected. All right. So just pausing there for a second, is that bringing any questions up in your minds? So like the chi-square formula, the chi-square table of critical values will also always be provided to you. You don't need to memorize it ever. But we're going to use it in the same way that we used the chi-square value in the correlation coefficient table. Again, if the chi-square value that you calculate is less than the critical value, we accept the null. If it's greater than the critical value, we reject the null. Okay. Degrees of freedom, that formula down here is also a little bit different, but it's also provided to you, okay? In this case, it's going to be the number of categories or the groups of observations that we've made, minus 1. That will be the degrees of freedom in this case. So it won't be unlike in the correlation coefficient analysis where it was the number of pairs minus 2. In this case, it's the number of categories minus 1. All right. So when we come back from our break, we will do a practice problem that I hope will be familiar to you. We're going to return to that koi fish pond and use data that comes out of that simulation to analyze the data statistically to look for significant differences between what we're observing through the simulation versus what we would have expected in the simulation as the simulation runs over the course of time. In many ways, we'll be able to actually analyze statistically whether or not evolution has taken place within this population of koi over time. So I've got 9:24, almost 9:25 on my clock. Let's take a 3-minute break and we'll come back and we'll do our chi-square practice problem. See you in a bit. All right, if we could start making our way back together. My hope is the graphic, the image on the screen looks familiar. I thought this might be a good place to begin with a practice problem that we can do together in respect to using the chi-square test to determine whether or not there is a significant difference between two sets of data, an observed set of data and an expected set of data. The College Board loves the chi-square test, and they have been implementing more and more questions using the chi-square test into the exam over these last couple of years. This first example looking at evolutionary change in the Hardy-Weinberg equilibrium is one of the places where the chi-square test is showing up. It's also showing up with animal behavior data. So if we have some time, we can either independently or together look at an example of how you might go about using the chi-square test to analyze animal behavior data. A third place where this test is used is in genetic experiments and data that comes out of genetics experiments. We're not doing that now, but just suffice to say, the chi-square test pops up quite a bit in this class. We will be returning to it later in the year. All right, so we've got our koi fish pond. And what I thought we could do here is first use the chi-square test to verify that if we don't change any variable in the simulation, that there is not a significant effect on that population over time. In other words, the population is not evolving under the baseline set of conditions. Okay, so because the simulation can be run pretty quickly, I thought what we could do is we could run it first for 50 generations. These values up here might change because this was a version of the, this is the time I ran the simulation once. Okay, but then we can run it a second time under the same conditions, right? So no change, to see whether or not there's a significant difference. Because ideally, right, if we're not changing anything about the simulation, there shouldn't be a significant difference between what we observe, whoops, and what we expected. And then we can come back and we can change a variable, one of the variables that you chose to change as an example. And then upon changing that variable, we can generate a new set of data and ask the question, okay, by changing that variable, how we generated a new set of data where now there is or there isn't a significant difference between the observed and the expected sets of data, right? So that's where we're going to be going. All right, so can you see the tutorial on your end? Okay, so my hope is here. All right, so baseline conditions, right? I'm not going to change anything. I am going to speed it up so that we save some time here, right? And I'm going to get as close to 50 generations as I possibly can. Got any good jokes? If I hit 51, I apologize. I'll do the best I can. Here we go. Can I hit it? Look at that. Perfect. All right, so 50 generations. Our population size is 200, but look, we also have some frequencies of each genotype, the homozygous dominant, the heterozygous, and the homozygous recessive genotype, okay? Now, be careful. When we do a chi-square test, right, we can't use frequencies. We have to use numbers of organisms, right? We have to use numbers of observations. But the good news is we know how many individuals are in this population. We also know the frequency of each individual genotype in that population. So with a little bit of math, we can actually figure out the frequencies that we're looking for, okay? So these values are going to be our observed values. So I might need to click back and forth a couple times, but I get a pen out so I don't forget them. We've got homozygous recessive at 0.31. We've got heterozygous at 0.5, and we've got homozygous dominant at 0.2. And we've got 200 individuals total in our population. So if I flip back here, all right, can you see this table okay on your end? Excellent. So our observed values are what we just saw, okay? It's what we collected in our experiment. But we're not going to enter the frequencies of the genotypes. We're going to actually enter in the numbers of individuals. And we can do that because we know how many total individuals there were in that population. So homozygous dominant, that was 0.2 times 200 total individuals. So that's going to be 40 individuals. Okay. Heterozygous, that frequency was 0.5 times 200. That's 100. And of course, that means that's going to be 60 because there are 200 total individuals in that population. But wait a minute. Where are the expected values going to come from? What do you think?
The allele frequencies.
Not the
The Weinberg equation.
not the, well, I suppose you could do that, but that work's already been done for us. In fact, the simulation is using those equations, right?
Maybe the starting numbers.
The starting frequencies, right? Now, remember, we haven't changed any of the conditions in the simulation yet, right? We ran it for 50 generations under those conditions, right? And these are the genotype frequencies that came out of the simulation as a result. They are our observations. But if we went back, and we can do this, right? If we went back, we set up the experiment again. In fact, I can even refresh the entire thing to go all the way back to the beginning. I'll pause it there before it hits. Do we know the initial genotype frequencies in that population before we even did anything? Help me. Help me understand. Help me understand if you're confused. It's hard. About 2/3 of you are totally black right now. I can't look into your eyes. I don't know if you're having a tough time. Thank you, Trevor. Do we know the initial genotype frequencies before we ran the simulation? They're right there, right? We know them. And if we're wondering whether or not, right, evolution has taken place, whether or not those genotype frequencies have changed, if we were to compare what we just did to what we had at the beginning of the simulation and did our chi-square test, we could actually mathematically, statistically verify whether or not a significant change has taken place. If it hasn't taken place, well, then evolution hasn't occurred. And if it has, that's quantitative, mathematical, statistical evidence that supports the claim that it has. Okay, so our other values here, let's see, we've got 0.22 and we've got 0.51 and we've got 0.27. Okay, so I'm going to flip back to our notes. Okay. This time we still have 200 individuals, but this time I've got a frequency of homozygous recessives, whoops, at 0.22. So that gives me 44. Oops, of course, I need to get my pen back up. Okay, our heterozygous frequency was 0.51, so that's 102. And let's keep the math simple this time around. 0.27 times 200 is 54. So there's clearly has been a change, right? The question is that change significant? We need to go past just this number is bigger than this number in respect to how we support our claim, and instead ask whether or not that difference is significant. Is it due to chance? Is it due to natural variation? Or is it due to something else? Something of consequence, something of meaning. All right, so if you've done the practice problems, you know what comes next. The math is not going to be very complicated. Looks like here we're going to have -4, and here we're going to have -2, and here we're going to have 6. We're going to square those values, so 16, 4, 36. And with your trusty calculator now, 16 divided by 44 is 0.36. 4 divided by 102 is 0.04, give or take. I'm going to round. And 36 divided by 54 is 0.66 or 0.67. And we can add those numbers together because remember the chi-square formula, right, is the sum sigma of the observed minus the expected squared of values divided by the expected value. So if you've done the reading and you've had some time to work on those 2 practice problems, you already know this. Well, we can add those 3 values together and we end up with 1.07. That's our chi-square statistic. What do we do next? What do we need?
Compare to the critical.
Bingo. We need those critical values. So, sorry for the mess, but I don't want to delete all of that writing quite yet. We have a chi-square value of what? It's over here at 1.07. Okay. How many categories are we working with in this analysis? You can hold it up with your fingers, or you can put it in the chat if your camera's off. How many categories, in fact, I can even click back. How many categories of data are we working with? Careful which finger are you next, right? There's 3, right? There's 3 categories. So degrees of freedom is 3 minus 1. So there's 2 degrees of freedom in this case. Again, that will always be given to you, even on the AP test. You do not have to memorize this. So we're at 2 degrees of freedom. Always safe to work with a probability value due to chance, due to natural variation of 0.05. If you want to be more stringent, you can. If you want to drop that to 1% or even 0.1%, that's okay. But usually we're pretty comfortable with a 5% chance that what we're looking at, right, is due to, or the difference between what we're looking at would be a better way to say that, is due to chance or natural variation. I keep saying that, right? I keep saying that. Natural variation. We started the year with that. It never goes away. It never, ever goes away. Okay, so it looks like our critical value is 5.99. So if I go back and I once again pull my pen up, chi-square crit, I excuse my penmanship, is 5.99. And we can see that the value that we've calculated is less than our critical value. So if our null hypothesis was a simple statement of that there's no significant difference between the observed and the expected values, can we accept the null? Or do we have to reject the null? Thumbs up, accept the null. Thumbs down, reject the null hypothesis. If the value that we've calculated for the chi-square statistic is less than the critical value, accept the null, reject the null. Sorry, I'm trying to check the chat too. Sorry. We should be able to accept the null hypothesis, right? Change has occurred, right? But that change in the numbers of individuals with a particular genotype, that change is not statistically significant. Okay? It's due to random chance. It's due to the existing natural variation within the population. What questions does that bring into mind before we move forward? Silence. Silence is so weird. Do you want to try one more together? Or do you want to do some independently, checking your answers as you go? Independent, together. If I hit record this video, it is recording. This will be up on Google Classroom. Yes, well, on my YouTube channel, but yes, you get to it through Google Classroom. Right, so I'm not seeing a lot of thumbs up. So let's try it one more time. I need the feedback, folks. So many of you have your cameras on. I actually don't even know if you're there. I hope that you are there. Okay. Independent work with some practice problems. I'll give you control of the slides. Okay. Another problem together. I'm seeing, thank you. Thank you for that. I'm seeing lots of thumbs up now. Okay. Can I erase what's on the slide? Okay. All right. So I think for the time that we have left, we've got about 10 minutes. I'm going to move you to a spot and then give you control of the slides. Because there's lots of different types of problems. Here's one here. All right, so I have chosen some different multiple choice questions from released AP exams that deal with the chi-square test. Okay, so this is one of them. If you keep clicking around, now that you have control of the slides, you'll find some more. Okay, I did try to organize them in terms of increasing level of difficulty. That's probably not a perfect hierarchy, but it's pretty apt. So if you think you've already got a handle on this, you might want to skip ahead, but take a few minutes here. We'll come back together, let's say in maybe 5 minutes, do a couple of these problems. And then if there's any that you want to talk about together before we sign off, we can definitely do that. And I, of course, am here to support you if you have clarifying questions. There is a short free response question in there as well. There's two. So push yourself a little bit. Try more than just the null hypothesis questions. If you're dying to look up the answers, they are in the Unit 4 notes. Get to that through Classroom. Fortunately, I can't reveal the correct answer with Pear Deck. It won't let me do that. But we can talk about the correct answers.
I was thinking of doing these things like 3 foot by 3 foot and having them outside, but. Okay, yeah, so this used to be part of. And I would salt sand and mix in minerals and stuff like that. It was an absolute pain in the ass to set up and for them to mostly just puzzle a whole lot and a long time. Yes, those were some of the minerals. Those were the minerals actually that I mixed in. And then, oh yeah, the shell casing. Yeah. Yeah, these different things. I even mixed in you're welcome to all this. Okay. I'm basically that as too much effort. Yeah. Too much last time.
All right, I want to honor the time that we have left. Is there a problem that you've gotten to that you think we could spend a couple of minutes talking about briefly?
The lizard one, I think.
So that's the on slide 91.
Yeah, the one you're on right now.
Okay. All right. So again, there's a chi-square analysis, kind of a funky question as a multiple choice question. Which of the following is the closest to the chi-square value? So that's kind of a weird way of asking the question. What we end up choosing might not actually be the calculated value, but is instead the closest value. A question came in through the chat about, okay, well, I've obviously got the observed values, right? They're given to me in the table, but what are the expected values? Well, the expected values are going to come from your Hardy-Weinberg equations, right? You know, in this case, the number of individuals that are homozygous recessive, right? Well, if that's true, you know Q squared equals, what's that, 10 out of 100? Total individuals. So Q is the square root of 0.1. Need my calculator here again. 0.1 square root. That's going to be 0.32, which means P is going to be 0.68, right? So if I wanted to know the expected frequency of, say, the homozygous dominant individuals, if this population was at equilibrium, and that's really ultimately what I'm trying to test, right? P squared, 0.68 squared, is 0.46, okay? I'm just using a calculator here. I'm not coming up with off the top of my head. So that means I expect 46 of these individuals to be homozygous dominant if the population was at equilibrium. For the heterozygotes, I'm talking about 2 times P times Q. That works out to be 0.44. So that's 44 individuals. And of course, I had my 10 individuals there. So if I set a chi-square table, I don't know if I have enough space, nor I'm not sure if we have enough time to do that, right? These are going to end up being your expected values. And you might just be able to imagine in your mind, if you went through and did these calculations, you're going to end up with a really big chi-square value. So of the choices that are provided to you, the value that's closest to the ones that are given, it's the largest value. I forget exactly what it is, but I can look at it real quick. It's D. It says 23.1. It's actually a value that it's larger than 23.1, but it is the closest to 23.1. But regardless, what you're ending up with, right, is a population that is far and away evolving, right? Because what you're observing versus what you would have expected to see if the population was at equilibrium, very different values. Okay, statistically significant values. So lots of practice problems with the chi-square test, okay? Before you sign off, if you could just quickly scroll ahead here, whoops, drag your dot. How much more practice do you think you need? So if we were to come back together on Monday, would one more practice problem be helpful? Would many more practice problems be helpful? Do you think you've got this? Drag your dot, and as soon as you're done, you're welcome to sign off. As always, thank you for being here. Thank you for your attention. No, this is not easy. It's not easy for me.
Thank you.
Thank you. Bye.
Take care of yourselves, everybody. Please.
Thank you. Bye.
Mr. Bergeron, I have a question. So if so you put the summative assessment 3 as a quarter 2 grade, right?
Summative assessment number 3 should be
No, as quarter 1, my bad, as a quarter 1 grade. So if the corrections go in as a quarter 2 grade, they'll still count like the same way, right?
Yeah, I mean, ultimately, as an 11th grader, right, it's the semester grade that's important to you. Somebody actually noticed this yesterday. They looked at Power Schools and they saw that they had like an A+ for the second quarter, and when the 2 quarters were averaged together, they had like a really high grade for the semester. Well, it's because the corrections are going in as something greater than 0, right? And that's extra credit. So your quarter 2 grade is like above 100%. So yeah, it's going to go in as quarter 2. It'll all work out in the end. It's just that the way the due date worked for the corrections, it fell on a Tuesday, which takes us outside of first quarter.
Okay, sounds good. And also, so you calculate the semester 1 grade by averaging the quarter 1 and quarter 2s?
No, it rolls. It's not an
Okay.
average. They're
It
just
adds them.
they're just weighted equally.
Okay.
I just wanted to, sorry, I came in early. I just wanted to let you know that I've got the because you told us to let you know if we've got missing assignments, and I just wanted to let you know I've got my missing assignments in.
Okay, but
Do I need?
you got to do more than that. You got to send me a message
Oh.
with the actual assignments, because that's
Oh, okay, got it.
I don't know what to look for. So please,
Okay, I'll write them down.
thank you. Thanks.
And
Sorry about that.
also, if I do corrections to my lab, if I finish them like by the end of the day, would you be able to see them or?
Number 6 or
Yes, 6.
I'll do my best.
Okay,
I'll do my best.
thank you.
Sure.
See you, Mr. Bergeron.
Take care. I'm gonna give everybody a new Pear Deck code here, so don't use the one on the screen right now. Give you your own, because you are your own class. Morning, everybody. Welcome. Hold on here. That is what we want. Now you should be able to see the Pear Deck code. Good morning, everybody. Welcome. Faces, whatever faces I'm allowed to see. It's like people were up really late last night. Not everybody, but a lot of people were up late last night trying to get work. I saw submission times of 2:30 in the morning.
That's also just flat out my sleep schedule. I need to fix.
Gosh, how are you functioning?
I'm not.
Oh, well, good. All right. I think we've got everybody. Welcome. I was sharing with another adult yesterday, an adult in our central office, a bigwig, if you will, how disequilibrating it is for me to stare at black backgrounds with white names every day. And that's not me telling you turn your camera on. That's me just sharing. It's still weird. Still weird. Even after a whole quarter together. All right. Plan for the day. I do have a check-in, but I want to offer to you. I've offered this to other classes as well. Yesterday I sent a text and I posted an announcement on Classroom about lab number 6. As I began to look at your work, I noticed that some of the statistical analyses were missing. So I wanted to give you the opportunity, if you'd like. I can certainly, once again, show you how to analyze that data statistically, with the understanding that if you want to unsubmit your work for lab 6, make some revisions, some additions, and then resubmit, you're welcome to do that. Would that be something, rather than doing the check-in this morning, that you'd like to spend a few minutes doing? Give me a thumbs up if that's a yes, a thumbs down if it's a no. And if you say nothing, I hope you say something. All right, now I see some more thumbs. Okay, now I'm seeing more thumbs. So it'll be a brief summary of how to do this for sure. But we can do that in lieu of the check-in. And the check-in, we can always move to a different day. It was hopefully going to be fun. It was going to be a scavenger hunt in your home based on a random object generator. So the first person to bring the random object back to the screen would have received a special prize, but we can do that another day. The rest of the day, we're going to be use that. Hopefully you had a chance to look at the homework for today, using a new statistical test to analyze a different type of data. And I've got lots of practice problems that we can use to develop a deeper understanding of that statistical test. I, of course, can lead you through one of those practice problems. And then we should have some time at the end of class today to give you some time to work. And we'll end everything together with a quick exit slip. But before we get started, what questions do you have for me or for the good of the group? Silence. Also very disequilibrating. Silence. You folks gonna be this quiet when we're back in person? No way. Oh, the idea of I'm entertained by the inability to like mute you all. That'd be fun. All right. So let's do this. Let me pull up my sample spreadsheet from lab number 5, and we can use that data to quickly review how to analyze these data statistically. Let's see, lab 6. Alrighty. Can you see the spreadsheet? All right, wonderful. So again, this was a sample spreadsheet, right? I chose to analyze the relationship between flower distance and collection rate. I also chose to analyze the relationship between flower distance and total nectar collection time, if you will. You don't have to do that for 2 sets of variables, right? 1 set of variables is sufficient. This is just sample data, right? Examples. I want to provide you with multiple examples. But all of the data that you're seeing on the spreadsheet, I think I said this in the video as well, it's coming right out of the simulation. I'm literally just copying and pasting. And then once I have assembled the data, I'm plotting the data using Google Sheets. I'm just going to use the collection rate versus flower distance data as the example. That's the first graph down here. All right, so we use our scatter plot to plot our data points. We use that handy feature in Google Sheets, the trend line feature, to draw our best fit line. Gone are the days where you are plotting data by hand and using a ruler to draw a best fit line. This is the 21st century. Seriously, we're still using paper. I think some people are. But what's also super handy about Sheets is not only will it draw the line for you, it will also give you this value of R squared, right? Now, in reality, the value of R squared is not super helpful because what we want to be using is the value of R, or the square root of R squared. So for this sample, I'm going to go ahead and just do this for B2, but you could certainly do this for B1 and B2. But if I've got an R squared value of 0.88, I need the square root of that value, and that works out to an R of 0.94. Oops. Now in reality, this is an inverse relationship, right? As flower distance increases, collection rate decreases. So really the value of R is negative. It's an inverse relationship, but we're not going to worry about that value in our analysis, or the sign on that value in our analysis. In fact, if we did, we'd always be forced to accept the null hypothesis. So we don't want to do that. So we'll just use the absolute value, 0.94, for our analysis. All right, so that was already a lot of me talking. Is this bringing any questions to light for you? I'm going to write down that value of R so that I don't forget it. 0.94. Because I'm going to go ahead and clear this out. And I want to do something with that value of R, right? I want to use it to perform a statistical analysis. But to do that, I need, there they are, my critical values, right? Because ultimately what I'm striving to do, right, is pose a null hypothesis, right? We did some practice around this last week. There is not a relationship, there is not a correlation, there is not an effect of variable 1 on variable 2, okay? And with this statistical analysis, what we're attempting to do, right, is test that null hypothesis. Can we accept the null? Can we reject the null? It's all based upon this analysis. Well, if our value for R, get my pen back up here. This is our calculated value, right? Was 0.8, oh, sorry, not 0.89, 0.94. That's a 4, I promise. What we want to do is compare that value to a critical value at a known number of degrees of freedom. I think I had 7 pairs of data, 7 data points. Okay, so our degrees of freedom always, always, always will be given to you. You do not need to memorize this. Do not waste your mental energy on memorizing stuff. Please. It's the 21st century. It's 2020. You are carrying computers in your pocket that are vastly more powerful than the computer that I used in college. Why? If anybody, any adult asks you to memorize something, the immediate question, respectfully, should be why? Seriously. Do never forget how much power you have in this. Seriously. So 7 data points, 7 pairs of data, degrees of freedom, number of pairs minus 2. So our degrees of freedom is 5, our R is R5, which gives us a critical value of 0.754. And you can see already, right? Our calculated value is greater than our critical value. And if that's the case, you can reject the null hypothesis, right? You can reject the statement that there is not a relationship, right? That there is no correlation, that there is not an effect of variable 1 on variable 2, and instead accept the alternative hypothesis that there is a relationship, that there is a correlation, that there is an effect. Okay? And all of that can be part of your evidence section. And then, of course, in your explanation, you're coming back to the science idea, which for this lab most likely deals with the transmission of information, right, within and between biological systems. Remember, I'm always trying to put the slide deck as part of the assignment post that has the information that you need. I'm modeling the process. But with the evidence in that science idea, you're building your explanation. So if you see a relationship that's significant, well, why? Connect that to the science idea. And if you see a relationship that isn't significant, why? Connect it to the science idea, right? This is what scientists do. They are not proving stuff ever. They don't spend their careers just verifying what's already known. They make discoveries. They test hypotheses. They gather data in support of those hypotheses with the hopes of convincing other scientists and maybe lay people, but those lay people are getting harder and harder to convince that what they found is meaningful. So again, a lot of me talking. Questions, comments, wonderings? Helpful? Not helpful? Kind of helpful.
If we unsubmit our lab, when should we turn it in by?
When you're done. Somewhere along the line, we became obsessed with grades. We forgot about the learning. And I get it, 12th graders, you've got deadlines. I fully understand that. We're going to take care of you. We're going to put you in the best light possible. 11th graders, take a breath. You're running this hamster wheel. And I would remind you, you actually have no idea which criteria colleges and universities are deciding upon when it comes to your admission in the first place. It's a black box. Literally, schools have to be sued in order to reveal their secret formulas. Okay? I hope you know by now. I got your backs. I'm gonna take care of you. I'm not gonna screw you. So really, make sure it's good. Take as long as you need. If it's after the due date, just let me know that you turned it in. I'll take a look at it, and I'll give you the points that you deserve. Been sharing with some other adults this idea of what's wrong with everybody getting an A+. They look at me curiously. I wonder what that means. Can I clear the screen with of the writing? Is that okay? All righty. Is it okay to move on? Gotta switch my slides over here a little bit. Kind of excited. The district purchased all of the teachers a license to Pear Deck. And I think when you do that, it works a lot better. Alrighty. Let's close that up. All right, so if you had a chance to look at the homework for today, much of what we're gonna do is gonna look familiar. So I'm not gonna lecture on the chi-square test or really even how to perform the chi-square test, because my hope is that you've had some practice doing so. But we can do a practice problem together that uses a different set of data. Actually, a set of data that you've worked with before in a previous lab experiment, albeit a virtual one, to analyze the data for statistical significance. Okay. So a reminder as we get started here that up until now, we've focused most of our effort on analyzing continuous data or data collected over the course of time. What this new statistical test allows us to do is analyze discrete data or data collected at one moment in time. So there's a difference. Continuous over the course of time, discrete one moment in time. All right. So these might be observations, right? The number of observations at one moment in time. They might be the number of organisms that are behaving in a certain way at one moment in time. Okay. So it's different. And for the most part, unless you've taken AP statistics, you really haven't had to think about these forms of data analysis before. Okay. So we are going to use this chi-square test. There is a chi-square formula. You do not need to memorize it. If you ever find yourself trying to memorize something for this class, you're probably doing it wrong. Okay. So even on the AP test, these formulas are given to you. It's how we use the formula that matters. Okay. So this one, I would say, is far less complex than the linear regression formula, but we didn't even use that formula either. We let Google Sheets do the work to calculate our value of R for us. There is actually a built-in formula into Sheets that lets you calculate the chi-square statistic as well, but the math is pretty straightforward, and I don't think we need to use it for our purposes. Okay, so before we move forward, does this bring any questions up in your minds? different type of data to analyze with a new statistical test. All right, the formula itself is not complex. Really, it comes down to calculating a series of values here, and then adding those values together. The Greek letter sigma, for all you sorority and fraternity sisters and brothers or future sisters and brothers, mathematically means to sum, to add together. So we're going to find the value in the circle and then add all those values together. And that's going to be our chi-square statistic. Ultimately, what we're striving to do is find a set of observed values. These values are probably going to come out of an experiment. And we're going to compare them to a set of expected values. These can be thought of as the control conditions, the baseline conditions. It really depends on the context of the experiment that we're performing. We'll do an example here in a second. Right? But once we have those values, when we do the math, what we'll get out is this chi-square statistic. And here's what's great. Once we have it, the process that we just used to do our linear regression analysis, our correlation coefficient analysis, it's going to be the same for our chi-square analysis. We're going to calculate a value of chi-square. We're going to compare it to a set of critical values for the chi-square statistic. And just like before, if the value that we've calculated is less than the critical value, we're going to be able to accept the null hypothesis. If instead the value of chi-square that we calculate is greater than the critical value, we're going to have to reject the null hypothesis. All right? And a reminder that when we're rejecting the null hypothesis, we're saying that there is a statistically significant difference between the groups, in this case, the observed and expected values that we are comparing to one another. Gone are the days where we're simply comparing two numbers to each other and saying this number is bigger than this number, so there's a significant difference. Okay. Those days are gone. They need to be gone. We can't keep doing what we've been doing forever and always. Okay. We need to ask the question, is that difference real, or is it due to chance? Or in the context of biology, to natural variation within the system that we're studying? Because if it is, even if that difference exists, in reality, there is no difference.
You might have gone over this already, but how do you know when to use the chi-square analysis?
Ideally, in a perfect world, the question will be worded in a way where it's actually going to tell you that. But if it's not, right, what you're looking for are clues in the question where the data was collected at one moment in time, right? That's going to make it discrete data. As soon as you see anything that is suggestive of the data being collected over the course of time, right? So if you've got rates, if you've got changes that are taking place over the course of time, the chi-square test is not going to be appropriate. And it takes practice, and you are not going to be perfect. You're going to make mistakes. You're going to analyze the data using the wrong test, okay? So that's where I come in, right? Feedback, revisions, fix. All right. A reminder though, before we, actually we'll take a break here in a moment and then we'll do our practice problem. But before we take our break, a reminder that the critical values are also going to be given to you. Okay, you do not need to memorize them. For the love of dog, you do not need to memorize them. Okay. They are going to be determined a little bit differently. If you remember from the correlation coefficient critical table or table of critical values, it was the number of pairs minus 2. If you don't remember, that's okay. That 2 would be given to you. The degrees of freedom for the chi-square test, it's the number of categories or the number of groups that you're comparing to each other minus 1. But that 2 will always be given to you, even on the AP test. Okay. But what we do with those values is going to be the same. We're going to calculate our chi-square value. We're going to compare it to the critical value. If it's less than the critical value, we accept the null hypothesis. If it's greater than the critical value, we reject the null hypothesis. All right. So there are lots of different practice problems that we can do together next after our break. I thought a useful place to actually begin that work would be to go back to a set of data that you actually haven't analyzed statistically yet. It's that koi fish pond data that came out of lab number 5. And I thought it might be useful to analyze that using the chi-square test. And then we'll do that together. And then with the time that we have left today, you can do some additional practice problems using the chi-square test. Does that sound like a plan? Or do you think you're ready to do the problems independently? Let's do a quick poll here. If you think you're ready for independent work, give me a thumbs up. If you'd like to do a problem together after our break, give me a thumbs down. You can do it in the chat too if you want to. You can just write down or down arrow. Or I get nervous when I see nothing from the black boxes. I hope you're still there.
Most of us responded in the chat.
You did. Thank you. All right, so let's take our break then. It's 10:25. We'll come back together right around 10:28 and we will tackle a practice problem together. I'll see you in a bit. Alrighty. If we could start making our way back together, please. Isn't it nice just to get up and move away from the screen for a little bit? I'm afraid to ask, but is it happening at least a little bit more in your other classes? I'm so sorry. Okay, well, shall we tackle a practice problem together? Okay. So again, I thought it might be helpful to go back to the pond to analyze a set of data, but I'll say there's lots of different places where this chi-square test could be used. And I've got lots of different practice problems in the Unit 4 notes that you might find helpful, because we won't have time to do them all today, of course. So they do show up in Hardy-Weinberg equilibrium analyses. That's why I thought Lab 5 would be helpful. They also show up in animal behavior settings. That's why it kind of fits here in this part of the unit. If you're wondering why we're not doing animal behavior, we could, and I've got a practice problem in there that we can analyze. It also shows up in genetics experiments, which we obviously haven't done yet at all, but we'll come back to later in the year, I hope. So it shows up in different places. And recently the College Board has really begun to ask more and more of these sorts of questions. So I want to make sure that you're as comfortable as you possibly can analyzing these sets of data. All right. So let's do it. Let's go back to the pond. Pause that real quick. All right. So if you remember this from a couple of weeks ago, right, you initially ran the simulation under the default, the baseline conditions, and then you changed a variable and you allowed the simulation to run again for 50 generations, or at least 50 generations. Some of you did more than that. And you collected data under the baseline conditions and then under the conditions that you chose to manipulate. Right? But then all you really did, right, because all you were trying to verify is that evolution had occurred, is whether or not the allele frequencies changed and whether or not the genotype frequencies changed. And some of you actually asked the question, do I need to analyze these data statistically? And I said, no, don't worry about it right now. I'm trying to take it easy on you. I got the sense that things were getting a little overwhelming. So this is why we're circling back. And we're going to now analyze these types of data statistically using the chi-square test. So if you're wondering why now, that's the why behind the now. All right, so what I'm going to do first, actually, is I'm going to go to the data. I hope you can see it okay on your end. And notice that my population size is 200 and that I actually have the frequencies of all 3 genotypes. Okay, these are my baseline conditions, right? So I'm going to go back here to my notes. And you're going to notice a couple of things here. I've got my baseline set up. Now these values may not apply because I actually ran the simulation separately away from you. But what we're going to do is we're going to use the values that are on this, or that are in the simulation right now, and we're going to use those values as our expected values. Okay. We want to do that because eventually we're going to run the simulation under the default conditions for 50 generations. And we're going to ask the question, is there a significant difference between what we would have expected initially and what we observed after the simulation ran for 50 generations? Because if there's a significant difference, well, that's evidence for evolutionary change. And if there isn't a significant difference, right, if we have to accept the null hypothesis, then that's telling us that that evolutionary change has not taken place. All right. So what's nice about this is we're still making the comparison at one moment in time, in many ways, before and after, initially and then after. You might even remember when we do these Hardy-Weinberg analyses, right, we're assuming at one moment in time that the population is at equilibrium, even if it's not. And then we're coming back later and we're reinvestigating that population to see if those allele frequencies, if those genotype frequencies have changed. And if they have, that's evidence for evolutionary change. If they haven't, well then the population has not evolved. Okay. So what I'm going to actually do here is I'm going to go back to the simulation. Since I have the frequencies of those genotypes, They're right there. Sorry, I'm seeing the chat as well. I'm trying to do two things at once. Of course. Person who asked the question in the chat, of course. We've got a homozygous recessive genotype at 0.22, and we've got a heterozygous genotype at 0.51, and a homozygous dominant genotype at 0.27. We want to be careful. We can't use those values in our chi-square table. Those are frequencies. They don't work. We can use the numbers of observations or the numbers of organisms. Well, wait a minute. This is kind of handy. I know how many organisms are in that population. There's 197. If I know the frequencies of each genotype in the population, I can calculate how many individuals in the population have each genotype, and those are the values that are going to go in my chi-square table. So if I flip back here, remember there were 197 individuals. These are my expected values, of course. So I'm going to have, we'll start here, 197. The frequency of those individuals was 0.27. Calculator. As a quick aside, you may use any calculator that you like on the AP exam. But 197 times 0.27 is 53 individuals. I'm rounding down. I can do the same work for the other ones. 197, my frequency of heterozygotes was 0.51. That's 100 individuals. And then my homozygous recessives, well, hopefully it's going to work out to, what's that, 47. So that's 0.22 times 197. It's 43. Did I make a mathematical error someplace? Oh, right. No, I didn't. It's the rounding error, right? That's 196. So it's 197 because it's not 197 because I didn't, because it's not 197 because I rounded is what I'm trying to say, right? So those are our expected values. Those are our baseline values, right? At time zero, if you will, at that moment in time. So now we want to run the simulation. We want to ask the question, okay, are those values going to change? And if they change in a significant way, the chi-square test is going to reveal that now, really in a matter of statistical significance, that population has evolved in a statistically significant manner. So just pausing there for a moment, is this bringing any new questions up in your minds? So far, so good? Okay. All right, so I'm going to pop back to the simulation again. But this time, in fact, I'll even refresh the whole page just to play it absolutely safe. Again, I'm going to keep the conditions as they are. I'll speed it up and let it go for 50 generations. Nothing more exciting than watching a simulation of Hardy-Weinberg equilibrium in real time. Think I can hit 50 dead on? I hit it last class. Oh, look at that. All right, so it's run, right? And these are going to be our observed values. Now notice our population size is a little bit different. It's 199. And we've got our genotype frequencies now. We've got our homozygous recessive at 0.2. It was 0.22. Our heterozygous is at 0.46, and our homozygous dominant is 0.34. So, right, there's a change. But the question is that change statistically significant, or is it simply due to natural variation within the system? Okay. So let's go ahead and pop back here. All right, again, this time, remember we had 199 individuals. So we'll do the same thing that we did a moment ago. Homozygous dominant, 199 times 0.34. That is 68 individuals. Okay. Heterozygous was 0.46. That's 91 individuals. And homozygous recessive, 0.2 times 197. Sorry, nope, 190. I want to make sure I'm doing my math right. Oh, I closed that one. That's okay. It was 199, right? Pretty sure it was. I'm gonna double check. 199 times 0.34. Yeah, okay, good. And then 199 times 0.46. Good. And then finally, 199 times my homozygous recessive at 0.2 is 40. Of course, my pen went away. All right. So we've got our observed values, we've got our expected values. Now we can fill in the rest of the table. And there are times where the College Board will ask you to do this. There are times where, and you'll see this in the sample questions that I have up in the notes, the question will be multiple choice, okay? Which means you're probably still gonna have to do this work, but then choose an answer from a list of given answers. All right, so 68 minus 53, that's 15, and that's -9, and that's -3. Let's see, that's 225. Biologists can do math too. That's 81, and that's 9. And then observed minus expected squared, 225 divided by expected is 53. So that's 4.2. And then 81 divided by 100 is 0.81. That I should have been able to do in my head. And 9 divided by 43 is 0.21. So remember, the formula is the sum of those observed minus expected squared divided by expected values. So we've got 4.2, oops, 4.2, wow, plus 0.81 plus 0.21. We're at 5.22. Okay, so again, pausing there for a second. Questions, comments? Bananas. Common ancestry, right? Just saying. You can tell no one's in the building because no one is responding to what I just did. It's still so weird. All right, well, we got our chi-square value. It's 5.22. What do we need to do next? What do we need?
Compare it to the critical value.
Absolutely. So it should be part of my writing on the slide. Okay. How many degrees of freedom are we working with here? You can hold it up with your fingers. Or you can put it in the chat. How many degrees of freedom do we have in this analysis? How many categories are there? How many groups are there? There's a hint in the bottom of the slide if you don't remember how to calculate it. And seeing answers change in real time. There's a homozygous dominant group, there's a heterozygous group, and a homozygous recessive group. So there's 3 categories that we're comparing. 3 minus 1 is 2. So there's 2 degrees of freedom in this analysis. Okay. So we move over to 2. That 5%, 0.05 probability due to chance, due to natural variation is always a safe place to start. You can be more stringent with your analysis, but you often don't have to be. Biologists are comfortable accepting the probability that 5% of the time, no matter what we do, the outcome of our experiment is due to chance and not actually due to whatever it is that we're doing experimentally. I know that sounds weird, but it's why we can't prove things. It's why we can only support things. Okay. But our critical value is going to be 5.99. So I can pop back over here. I can bring my pen up or not. So our critical value is 5.99. And you can see that 5.22 is less than 5.99. So we get to accept that null hypothesis, right? That there is not a significant difference between the expected and the observed values. Initially, compared to 50 generations later, there's been a change. We can't argue that there hasn't been a change, but that change is not statistically significant. It's due to natural variation in the population. It's due to random chance. Okay? So that's how you would go about solving a chi-square problem using that type of data. If you do the practice problems for homework today, they tell, of course, with playing cards, different type of data. The more practice, the more better. Are you ready to do some independent problems? Thumbs up if you're ready for some independent work. Thumbs down if you want to do another problem together. Or you can put things in the chat if you can't turn your camera on. Okay, I'm seeing more thumbs. I'm seeing a thumbs down in the chat, which is okay. I'm seeing mostly thumbs up. So if I can support the person with the thumbs down, we can move into a breakout room for these next couple minutes if that would be helpful. Otherwise, here's what I want to do, maybe 2 people. Let me first clear the ink. Is it okay that I clear the screen? No one's screaming at me. Okay. What I'm going to do is move you to a spot in the slide deck where there are some problems that you can practice with. It's all different types. So if you don't get to all of these, of course, don't feel like you can't come back and practice some more. All right. So another type of practice problem. You have control of the slide deck, but give yourself a few minutes here. We can certainly come back together in about 5 or 6 minutes and go over it together, but give yourself a minute to answer this question to the best of your ability. If you would like, I can set up a breakout room. And if you were somebody who elected down, thumbs down a moment ago, I will invite you to that room. If you want to join, that's great. If you don't want to join, that's okay. Hello.
Hello.
Is there anything I can help you with in these last few minutes, or are you getting stuck?
I don't really know. Like I understand it, but I feel like when I try to do it, sometimes I get confused.
Which is normal. This is new. So what I would recommend is there's different problems that you can look at. Some of them are earlier. So since you have control of the slide deck, if you kind of move back, there are some questions on null hypotheses. That might be a place to start to build your confidence. And then when you get to the problem like the one I started class with a moment ago, that might give you a little bit more, lack of a better term, more confidence solving that problem. I think the hardest part for students as they get started with this is not the observed values in the observed column, it's the expected values. So my hope is we'll have a chance here to do that problem together, and that may also provide you with a little bit more confidence. But why don't, since we only have a couple minutes, why don't you find one of the two multiple choice questions that deal with the null hypothesis? Just kind of click back a little bit and try to answer those questions.
Okay.
Okay. So I'm only seeing 4 responses thus far. Are you stuck? Stuck? Not stuck, just working. Okay. We only have a couple minutes left. Would it be helpful for me to kind of walk you through briefly how to solve a problem like this? No, I'm seeing the thumbs up and the yeses pop up. Okay. So it'll be quick, okay? So I want to make sure that you have, we honor the time that we have left. All right, so quickly here, you are given observed values, right? So they're going to go in your observed column of that chi-square table. The question becomes, where do the expected values come from? Well, the scientist, right, is wondering whether or not the population has evolved. So if the scientist assumed that the population originally was at equilibrium and then came back and made those observations in the table, well, the equilibrium values would be our expected values. So those values are going to come from your trusty Hardy-Weinberg formulas if you made the assumption that the population was at equilibrium to begin with. So when you do those sorts of things, you always start with the homozygous recessive individuals. So in this case, Q squared would be 10 out of 100, or 0.1, which means Q, right, is the square root of 0.1. That's 0.32. And that means P, the frequency of the dominant allele, is going to be 0.68. Okay. So you might recall that P squared is the frequency of homozygous dominant individuals. So 0.68 squared, that's 0.46. We already have Q squared. Our heterozygous frequency, genotype frequency, would be 2 times 0.32 times 0.48. That's 0.31. Now we can see there are 100 individuals in this population. So using our frequencies, we expect there to be 46 individuals that are homozygous dominant, right? 0.46 times 100. And we expect 31 individuals to be heterozygous. All right. So those become your expected values. When you work through the math, you can probably already see it, right? You're going to end up with a pretty big chi-square value. So the answer to this question ends up being D. In fact, the value that you calculate is even greater than D, but the question asks for the value that's closest to the ones that are given. Regardless, the value that you calculate would force you to reject the null hypothesis and to accept the alternative hypothesis that there is a significant difference between the observed and expected data. Okay. All right. Well, there are lots of practice problems in here, so if you want to take some more time to practice, you're welcome to do so. Before you go, if you would quickly drag your dot to get a sense of what we might do on Monday. How much more practice do you think you need with these types of problems? And once you drag, you're welcome to sign off.
Thank you.
Thank you. Bye.
Thank you very much.
Hi, I just wanted to rejoin because I had a question about the 2 summative assessments.
Okay.
I think I also sent you an email. I think the thing closed.
Yeah, I closed them. Which ones do you need access to? Number 2 and 3?
Yeah, 2 and 3.
Are you going to plan to do them today?
Yeah, but that's what I was planning to do during lunch.
Right. So I will open those up for you and give me 2 minutes and they will be available.
I think everything else is updated at this point. Yeah.
Okay.
Massive checklist.
Yeah, well, could you send me a list so I know?
Yeah, I sent you an email, I think just before class.
Awesome. I haven't checked that yet. I will do that. I will do that at lunch.
Thank you.
You're welcome.